Swayam Prabha. Digital India. Educated India.
Okay, in the last previous classes, we were looking at continuous Markov process, and in particular, we talked about the Wiener process and the Ornstein-Uhlenbeck process. Okay, and so those are some standard, very useful continuous Markov processes, mainly aimed at describing Brownian particle position, velocities, or Brownian particle in a harmonic trap, etc. Now, in the context of chemical engineering applications, there are a bunch we can apply these theories. For example, sedimentation is one such example. In chemical engineering, in particular mechanical operations, we deal with solid liquid systems. Okay, and our aim here is to separate fine particles from a liquid. This will do either by sedimentation or by flotation, okay, depending upon the density differences. So clarifiers, decanters, or such unit operation machines and instruments where we look at this kind of sedimentation problem. So in those examples, we mostly apply these empirical concepts or single particle fluid mechanics based problems to understand the sedimentation rates, hindered settling, free settling, lot of regimes. So in that background, we can actually look at that problem from the continuous Markov process point of view. So the system that we are thinking about is something like you have a large column, okay. It's made it as a rectangular column. So we say that this we take as z direction, this is as x and this is y, okay, and then we are basically filling this with a liquid. In this liquid you have some suspended particles. Suppose if these particles are large, okay, like millimeter size or maybe centimeter size, and if they are dense, immediately once you prepare the solution, you will see the entire thing getting sedimented. Okay, like for example, if you take sand particle, okay, with the initial shaking, and then if you let it stand, in few minutes you will see everything settles down. On the other hand, if you have very, very tiny particle where the gravitational force is not very strong, okay, then you will see a very well suspended uniform concentration of particle throughout the z direction, okay, because Brownian motion will make it well mixed, and then you will have a very uniform composition for the entire height. Okay, so we are talking about very small size where gravity is not playing a role, leading to a uniform distribution, and then you have another case where the particles are big enough that the gravity will make them sediment or float immediately. Okay, those are two extreme conditions. There is another domain in which the particles are not neither too small nor too large, where there is a sufficient Brownian motion. At the same time, the particles are subjected to gravitational field. So in this case, the concentration profile will not be uniform. It will not phase separate. You will get an equilibrium distribution based on certain profile. So our task here is to look at that particular problem, that you have a Brownian particle in a gravitational field. What is the equilibrium distribution of the particles? So directly applicable to chemical engineering, as I said, sedimentation, floating, etc. This problem we want to again approach from the continuous Markov process point of view. In other words, the Fokker-Planck formulation. Okay, so we know the structure of the Fokker-Planck equation. We just need to find what are the characteristic functions are. What is this drift A? What is the diffusion term A, B, and so on. Okay. In this problem, obviously it's a three-dimensional problem, but if you look at the gravitational effect, it is going to be only on the z direction. If I take any particular plane here, okay, the xy plane, in the lateral xy plane, it's a free diffusion. there is no gravity in the given xy plane. So there the concentration is going to be uniform whether I take the xy plane here or here or here. In that plane the concentration is going to be uniform. So there is no need to solve the problem in xy plane, but across z you will see a concentration being affected because of the competing effects of the diffusion and the gravitational force. Okay, so that's what we wanted to investigate. So before we set up the Fokker-Planck equation for this problem, to understand what the drift terms are, what is the diffusion terms are, we again look at an individual particle, Brownian particle in a gravitational field, set up the Langevin framework, and then identify the terms for drift and diffusion, and that goes into the Fokker-Planck equation. So the problem is sedimentation. In other words, it is actually a Brownian particle in the gravitational field. So how do we write the Langevin for this problem? Okay, imagine you have a particle somewhere here. So the dynamics of that particle so there is going to be a drag. Okay, so basically you write the Langevin equation just like how you would write for a free Brownian particle, but just add the gravitational effect. So here you have gamma dz by dt. So here the z is the z position of the particle. Okay, as I said, I am just doing only one dimensional. If you want to do the other dimensional, you have got to write the same Langevin equation in xy direction with no external field. It's going to be a free Brownian particle. So then we have this is going to be the gravitational force acting on the particle in the z direction. Okay, so then we have the thermal noise. This is a Gaussian random variable with 0 mean and unit variance. This is the random noise imparting a force on the particle due to thermal noise, drag, external field. This is written for z direction. So now we look at the overdamped approach, overdamped limit. Meaning we ignore all the inertial effects, we look at only the overdamped limit. So the sum of all these forces has to become 0. So we say that dz by dt is equal to minus mg by gamma delta rho by rho plus so here this delta rho is rho minus rho naught, which is the density difference between the particle and the background fluid, the medium. So here you can see that the rate of change of the particle position. Okay, so here I am talking about Langevin equation for the particle position in z dimension. So you got a drift term here. This is what A for us, and whatever you see within the bracket. So by the way, so here you will have 2 kBT by gamma. This is nothing but d. So you get 2d here. Okay. So by looking at this term is A. And B is the one within the square root, which is 2d. So now you can see that when we look at the Wiener process where A was 0, B was 1. Then Ornstein-Uhlenberg process where A was given as some minus some constant times x or the random variable itself, B was a constant. So here we have a third case where both A and B are some constant and A is negative, okay, in this case. Because we are thinking about a denser particle, so it will sediment, so delta rho is positive, everything else is positive, so the A is going to be a negative value. We can actually group all these terms and then we simply say this is equal to minus C. C is a group of terms given here. So now we can go to the Fokker-Plunk equation. And our aim is to find the probability distribution function for the position of the particle as a function of time t. Okay. So here we get so once you substitute A is equal to minus C, there is already another minus, so it becomes plus C here. C is a constant, comes out of the differential, and here you are going to substitute B is equal to 2D, 2 gets cancelled, you get D times this. Now this equation will tell you how P is varying with respect to Z and T. And to solve that, you need an initial condition and 2 boundary conditions. The actual derivation of this equation, where you get P of Z comma T, is given in Chandrasekhar's paper. The reference I have given in my notes. But in this class, what we will do is we will not be interested in this P of Z comma T, but we look at the equilibrium distribution of this. When time t tends to infinity, what does the equilibrium distribution of this is? Okay. So at equilibrium, this is set equal 0. So then we have C dou P by, actually we get dP by dz plus so I'm taking one derivative out and I get, so this I'm writing as I'm taking d by dz out, then I'll get Cp plus d dP by dz, this is equal to 0. So if this has to be 0, that means this whole thing has to be a constant, right? At equilibrium, when I'm looking at the equilibrium distribution of this P of Z comma T, it gives me the fact that this group of terms, the constant C times P plus D times dou P by dou Z, this term, the whole term has to be constant. So we say Cp plus d dp by dz is some constant f. Okay, so this is a constant. This is an unknown constant. We will have to find out based on some boundary conditions. So with this, we can solve this. So we get dp by dz plus c by d p yeah. So the solution would be p is equal to f by d into e power minus c by d z, something like this. D should get cancelled. F by c. Now let me just check the notes. The equation you will get is yeah. So actually you'll get f by d plus some constant g times e power minus c by dz here, where this is an integration constant. Yeah. So now remember that this is the equation that we are trying to solve, and if you look at this, we can also write this equation as dou by dou z Cp plus d So what you get in this entire term here, this is nothing but the flux J. Okay, and now why I am saying this as a flux is because now I am going to invoke the boundary condition that when the particles actually sediment here, when they reach the boundary at z equals 0, the particle cannot go further. Okay, it can only get reflected. Okay, so here this is basically like an impermeable boundary for this particle. Okay, so we say that the flux is 0 at this point. Okay, we are basically imposing that the boundary is reflecting and the flux, mass flux here is going to be 0. Okay, so we say that J is equal to 0 at z equal to 0. I am invoking this boundary condition so I can get one of these integration constants. Yeah, f by c is it? Can you just check, because in my notes I have f by d. F by c is it? Okay, okay, maybe it's a Oh yeah, because I think D will get cancelled, you'll get C. Okay. So you get F by C here, like this. Okay. Yeah, I think this D will get cancelled, you'll get C. Okay. Okay, so what we want to do now is we want to apply this boundary condition that at the bottom of the container, particle cannot go through. Okay, so it's basically impermeable. So here we say the flux of the particle at boundary is 0, that is this flux J is 0 and J is nothing but this entire term. Okay, so now what we can do is we can substitute. Now we know what the expression for P, so we write C times P is nothing but F by C plus G e power minus C by d Z plus d time the derivative of this with respect to Z. So you get G and this entire thing has to be 0 when Z equal to 0. So you put 0 here, 0 here. So here we have F plus G minus, oh sorry, so you get F plus GC because you're going to multiply. So here I'm multiplying with C, so I'll get F here plus GC, this entire term is 1 minus D gets cancelled, you will get GC, this whole thing is 1 now, that is equal to 0. This basically means F is equal to 0. The constant F that we mentioned here, that is basically 0. Okay, so then P becomes simply just this. Now this P which is given as G times e power minus C by d Z, what can you say about this constant G? How do we find G? Yes, you're going to normalize it because it's a probability distribution function. The integral of this over Z0 to infinity, that should give you 1. So what is G then? So if you apply the normalization condition, you will see G is nothing but C by D. So P of Z is given by C by D e power minus C by D Z. So at equilibrium, the probability distribution of this particle, single particle, will follow an exponential distribution. That's what this means. Now you can also substitute for the value of C. C is a constant. This constant C was delta rho by rho mg by gamma. This is a constant C, and the C by D here will be delta rho by rho mg gamma D. So let's say what's the unit of this quantity C by D? Okay, what would you expect? What should be the units of C by D? 1 by length inverse. Okay, so that kind of sets a length scale, which we call this as a sedimentation length. Okay, so that's a length over which concentration profiles are going to be varying. If that length is very small, then we know that the concentration is going to be pretty much uniform. If the length is very large, then it's going to have a wide distribution in the column that we are talking about. Okay, so the C by D, we are going to call this as LG inverse. That is the sedimentation length scale. So therefore, P of Z is written as 1 by Lg e power minus Z by Lg. So if you want to plot this, so here I am looking at Z equals 0 and this onwards, and you would expect that this to follow some sort of an exponential distribution, right? And the rate of this decay, that is going to depend on this Lg, and this Lg depends on all this parameter. What is the mass of the particle, what is the density difference, what is the drag coefficient for the system, and so on. So, okay, so all the material property of the system goes into defining Lg. So depending upon the value of Lg, you will have either this kind of decaying function. Okay, sorry. So this is basically concentration. This is rho. So when Z equal to 0, it has a maximum value, and then it kind of decays. Most of the particles are settled here, and then it goes like this. You have very fine particle, you may have very slow decaying. If you have a very high particle, you may have something like this, where everything is kind of settled very quickly. Okay, so the rate of this decay, this slope of this curve, the rate of this exponential decay is governed by this Lg factor. Lg is a material property, like I said, depends on the density difference, mass, drag coefficient, and so on. So this is a steady state distribution. The original problem, when you solve this total problem here, you will get time evolution of these functions. Okay, so that you can refer to Chandrasekhar's paper on the full solutions. So what we have done here is for our single particle and the probability of finding one particle and its distribution. Now we can also convert this into concentration profile, if you like. Okay, so let's say that initially we have so let's say you have n particles in a volume of V. Okay, so that's a volume of the liquid in which n particles are dispersed. So we can define C naught as n by V. This is the concentration we define. Now we can write concentration as a function of Z as C naught times P of Z. Okay, in other words, this is going to be C naught by Lg e power minus Z by Lg. So what we are saying is, you can actually solve this problem. We are thinking about a collection of n particle in volume V, but here each particle is undergoing a dynamical motion on itself. It doesn't interact with other particle motion. So if I assume that the system is very dilute, so the interparticle distances are too big that the particles do not interact with each other, then I can look at single particle dynamics like we did now, and then we map this into an n particle system by defining concentration and then correspondingly the uh, the concentration profile as a function of z. Now, in reality, when you have very high volume fractions of particles, high concentration, the particle relative motion and interaction between the particle can also influence each other. That ingredient we have not put in this theory. Okay. So, if you want to study hindered settling or high volume fraction settling, what we need is in the Fokker-Planck equation, we need to have additional terms to take into account of the mutual particle interactions, how each particle will interact in terms of their forces of interactions, and they can actually affect the dynamical motion. Okay, but in here we are talking about dilute case, and single particle dynamics can be used to calculate a concentration of n particle system, provided it's all dilute. Okay, so now I want to kind of slightly discuss something other than this. Of the three problems we discussed, the Wiener process, OE process, and now the sedimentation problem, in some cases we have this steady state solutions or equilibrium solution like this one, where the time, you're looking at time t going to infinity, and what is the spatial distribution of the Brownian particle or any other things. Okay, so now we would like to ask a question that in which kind of Markov process there can be a steady state or an equilibrium solution. Okay, so we can actually set up a small criteria based on the function a and b, and we can tell whether this function will have a steady state solution or not. Okay, for example, the OU process also has a steady state distribution, because OU process, if you think about it, it characterizes the velocity of a free Brownian particle, and the velocity distribution takes a steady state or equilibrium distribution following Boltzmann distribution. Similarly, if you take a Brownian particle position in a harmonic field, which also described by OU process, it also has a steady state solution, and here sedimentation also has a steady state solution. So there are some problem which has steady and others don't. Wiener process do not have. It just keeps evolving with the time. Okay, so therefore we would like to think about a condition mathematical criteria by looking at the functions a and b, the drift term and diffusion term. Can we say whether this problem will have a steady state solution or not? Okay, so that is something I want to present it here. It's just a mathematical treatment, so which will allow us quickly to say which problems are steady state solutions. So we start with the general expression for the Fokker-Planck equation. So we write this as dou by dou x E of xp this is a Fokker-Planck equation in general sense. So now we are seeking a condition where this term goes to 0, so that I can look for steady state solutions. So when this is equal to 0, we say that minus dou by dou x E of x comma p plus 1 by 2 So I'm rewriting this. So like before, this entire term, this entire term has to be a constant. Okay, we say this entire term is k, some constant k. Only then this condition is valid. So let's write that now suppose if in this case you actually need two boundary conditions. Okay, at two x values you need to have boundary conditions. Suppose if one of the boundary condition is reflecting, like the way we saw in sedimentation problem, at x equal to 0 or at x equal to some other value, then this constant k will be 0 for at least one reflecting boundary conditions. So then we can write 1 by 2 d by dx is equal to axp. So let's rewrite this. So what I'm doing here is I'm separating the variables here. Dx goes there, and then on both sides I'm dividing by bx times p. Okay, here and here. So on the right hand side the p cancels. Then you are basically left with 2ax b of x dx. So integrating this, you will get ln of b of xp is equal to integral of 2 with some constant c here. So obviously this function, when we apply normalization condition, that is p of x dx, this has to be 1. So this we can use to calculate this constant c, unknown constant c. Okay, so we say that c by b of x e power integral so we use this as dx prime so the integral of this entire quantity, that should be equal to 1 by normalization condition. In other words, c here is given by 1 over this entire integral. Now we have to say about something about this constant C. What is the range of value of C can be? Can it be 0? Can it be 0? So this, for remember, this C comes as a normalization constant in the probability distribution function. Okay, so this is a finite quantity. If it is 0, this becomes a trivial distribution of P equal to 0, which cannot be, which is not allowed. Nor C can be infinite. Okay, so C has to be some finite number in the range 0 to infinity. So now, for a given function A and B, right? For a given function A and B, you get this integral, and then do this other. Okay, by the way, there is another dx here, and then you have to calculate what is the value of C. If the C is a finite quantity from 0 to infinity, more than 0, less than infinity, then this will have a steady state distribution. If C is 0, then this is not valid. Such a problem will not have a steady distribution. Okay, so this is a mathematical condition that we need to work with. So now let's consider Wiener process, OU process, and other sedimentation problem, for which we know what the values of A and B, and then we can find what is the value of C. Okay, I will try to do it in the board, but you can also do it yourselves. Find out the value of C for Wiener process, OU process, and then see that when steady state solutions are allowed and when not. The standard Wiener process has A equal to 0 and B is equal to 1. So here when I substitute A equal to 0, this entire term becomes 0. So e power 0 is 1. Then you are basically left with 1 by b of x dx. B is constant, 1. Okay. Then what happens? You get integral of just dx, and you have this integral going from minus infinity to plus infinity, because in the Wiener process the range of x value is from minus infinity to plus infinity. Okay, so that will basically make it as yeah, A is equal to 0, yeah. So this will make C equal to 0. And therefore we say that the Wiener process does not have steady solution. But if you consider the OU process, where we say A is equal to some minus kx and B as some d or 2d, yeah, just d. So first we will calculate this e power 2a sorry, just exponential term. This integral here becomes minus 2kx by d. So you get minus kx squared by d. So when you substitute that e power minus k square d and then integrate this, you will get c as square root of kd by pi. So c happens to be a finite constant in the limit 0 to infinity. It's not 0, it is not infinity, it is a finite quantity, positive quantity. So then OU process will also have a steady state solution. You can also substitute the sedimentation problem where we had A is equal to some minus C and then B is equal to D. That will also, you will see that C will have a finite value. Okay. So when you try to model any continuous Markov process using Fokker-Plunk equation, the first thing for us is to understand what these characteristic functions A's and B's are. And to find out that, you set up the equation from the Langevin approach. You find the drift term, you find the diffusion term, then you know what A and B are. Then immediately you apply this condition and see whether this particular problem has a steady state solution or not. Okay, if this satisfies, then you can immediately look for the steady state solution rather than the dynamical solution. Yes, it's going to continue to evolve. Yeah. You can look at all combinations. A is 0, D is not 0, and D is non-zero, A is 0, all combinations. You can also have some process where this can go quadratically also. Okay, and it is also important that the range is also important. What range of random variable you are looking at, whether it's from minus infinity to plus infinity or 0 to infinity. For example, in the case of sedimentation problem, this integral will go from 0 to infinity. Okay, because one boundary is reflecting. So I hope this would be something useful for you to, maybe you can also make use of this in the project that you're doing to assess which problems do have stationary solutions. All right, so that's all I got today. And the reference for the full solution of this problem, I have given it my notes for you to look into it. There are also some plots that you can see.